So sample problem 3, again, has two parts. So this first part wants us to calculate the fundamental frequency. It gives us the length of the string, so we're going to start in the same way. Fundamental frequency, smallest we can have, so that is half a wavelength in the length of the string. We know the length of the string is, from our problem, 1.35 meters. As we looked at before, half of a wave will fit in that length, so you can think of it as half of the wavelength is equal to L, or you can think of it as 2 lengths of the string is equal to the wavelength. So we'll go about this in the same way. I'm just going to work through it really quick, not really explain all the steps. V equals lambda F 100 meters per second, that's with 2 sig figs, is equal to the wavelength. This we have because we know that there's half a wavelength, so 2 times the length of the string. Again, this is the first part of that problem. And we're looking for the frequency. And you should get 37.0. And that would be hertz. Okay, so the second part of this question wants the frequency for the fourth overtone. Now, a lot of people start getting confused when we get to overtones because they can be called overtones and they can also be called harmonics. So the first frequency, the fundamental frequency, is what is called the first harmonic. So there was, I think you guys saw this you should have seen this on a slide a few pages ago. First harmonic is the same thing as a fundamental frequency. Second harmonic is the same thing as the first overtone. So second harmonic, you can fit another portion of a wavelength. So that is, I'll bring it over here so you can see that. In the second harmonic, that is 1 wavelength. So the third harmonic is the same thing as the second overtone. There you can fit 1.5 wavelengths. We right now want the fourth overtone. So fourth overtone would be the fifth harmonic. So as we keep going, fourth harmonic, which is the third overtone, that fits 2 wavelengths. And then the fifth harmonic, which is what we want. So the fourth overtone, you can fit 2.5 wavelengths in the length of the string. If you were to invert that to figure out how many lengths of the string would equal the wavelength, that is 2/5 times the length of the string. So that's what we want. We're trying to find the frequency of the fourth overtone. Fourth overtone is also known as the fifth harmonic. Okay. So fourth overtone, again, it's a string, so there's a node at either end. We know the length of the string. That is 1.35 meters. And like we said before, there's going to be 2.5 wavelengths in that length of the string. So let's see. 1 wavelength, 2 wavelengths and a half. So maybe not exact drawing, but we're going to get 1 wavelength, 2 wavelengths and a half in the length of that string. I'm going to go ahead and finish it so it looks like a standing wave. 1 wavelength, 2 wavelengths and a half. And what we can say for the fourth overtone is that 2.5 wavelengths is equal to the length of the string. Or if we want to write it a different way, we can say 2/5 of the length of the string is equal to 1 wavelength. Okay, so if we broke this apart into 5, 2/5 of that is a wavelength. So same way as we did before, V equals lambda F. We have our speed. I'm going to use this here, this one, that the wavelength is equal to 2/5 L. If you want to first find the wavelength using this formula and then use this formula to get your wavelength, that is totally up to you. You can do it however you want. So I'm going to go ahead, 2/5 times the length of the string, 1.35 meters, times F, and then you'll calculate.